Hi, Math 1 students. This is Mr. Dobner, and we're in a brand new module, module number 3. We're going to be looking at the 3.1 Ready, Set, Go notes. This is thankfully some review. We will be graphing linear and exponential functions. So with linear functions, we're going to go back to our very familiar slope-intercept form. So we have y equals mx plus b. Or, of course, we could have y equals b plus mx. The key features that will help us make the graph is m is the slope. Remember, m tells us that we are moving with a rise over run. We'll talk about that and review that again. We also have the starting point, 0, b, which actually is the y-intercept. So this is not new. We've just been doing this quite a bit. We also have some review with the exponential functions. Generally, you'd see y equals a times r up to the x power. We're going to have a starting point to help us graph these exponential functions. The starting point, 0, a, and we also have the common ratio. The common ratio is r. So let's jump in and actually get some review here. This is kind of nice for us to get started. Graph each of the functions, name 3 points that lie on each graph. We'll do that underneath. Choose a scale for your graph. This obviously is y equals mx plus b, or you could write y of x if you'd like to. I think a lot of kids do that. I do that too. So you can see that our m here is going to be a 2. And whenever your slope, your m, is going to be a whole number or an integer, we can divide by 1. And this is going to tell us our rise over run. So we're going to be going 2 steps up when this is a positive. We're going to go 1 step to the right. But we also have a point here. We have the y-intercept. It's a -3, so we'll have 0, -3. So we're going to get graphing this very quickly. And I'm going to go ahead and make the axes jump out here, and we have our y-axis, we have our x-axis right here. Remember, b, which is right here, tells us to begin. We begin with this point 0, -3. So we'll go 1, 2, 3 steps down. And of course, as we're looking here, you can pretty much see that our scale is going to be going by steps of 1. And then what? We're going to use our slope. We're going to rise up 2. We're going to go up 2 steps and go 1 step to the right. We keep doing that. We can go up 2 steps, 1 step to the right. We can go up another 2, 1 step to the right. We can finish this out. Just as well, your slope could have been thought of as -2 over -1. If you'd rather, you could go down 2 steps and 1 step to the left. And of course, this linear function will look like a line. But they will want us to list points. And they've asked us to list 3 of them. Now, of course, I've written them very clearly on the graph here. We started off with this point of 0, -3. We can see right here we've got the point right next to it, 1, -1. And then we're also going to have this point right over here where it's 2 steps to the right, up 1, so that's 2, 1. Of course, you could very quickly write others, but we only need to write 3, and this would suffice. Let's take a look at number 2 real quickly. This is clearly an exponential curve. We could have y of x, or y is equal to a, then we'll have r to the x. And we're going to need a starting point. You know, our starting point is coming from the a here. So, you know, you can have, here's your x comma y, we'll have 0, 27. And guess what? We're going to have also a common ratio. Our common ratio, guys, is 2/3. Now, you could build yourself a table right now, and in fact, what you're going to do with this common ratio is just continue to multiply by 2/3. Now, if you've had some trouble working with fractions, be quick to use your calculator and get some support. You can say 27 times alpha y equals is how you can get a fraction. And we can get this worked out very quickly. So 27 times 2/3, guys, you can see you're going to get an 18. And then what? We'd keep multiplying by 2/3. We could say 18 times 2/3. And we will get 12. Let's do another, you know, just to see what's happening, is we just keep using that common ratio, doing what we've been doing for months now. This is how we, you know, started off even module 1, working with that common ratio, continually multiplying by whatever that value is. Here it's a fraction of 2/3, and that's definitely okay. You can see then we're down to an 8. So we've got a whole bunch of points, and hopefully we can see quickly where we're going. So let's get this graphed. I'm going to go ahead and sketch out our axes right over here. So we've got our x-axis, we've got our y-axis. I'd like to go up as high as 27. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. I'm also noticing 27, 18, and 12. These several outputs, these y values, are multiples of 3. And that could help us get as high as 27. So I'm going to go by steps of 3. This is just one way that you could scale, but it's going to allow us to represent this highest y value that we see right here. With my x values, well, you know, maybe I want to go every other space just to have a little bit of room here. You know, we could have just gone every tick mark being that distance. But let's see where we're going. 0, 27, we're way up here. 1, 18 will be right over here. 2, 12, 2 to the right, go up to the 12. 3, 8. Now, you know, of course, we're going to have to eyeball this, do a little approximating. It's going to be just below the 9, so maybe about right here. And you can see this is not a straight line, although it's looking quite a bit more linear than what we've seen in the past. This is still going down, and it is going to come down to the x-axis. We're going to see that in general, these exponential curves are going to get closer and closer to the x-axis without touching it when we have this a to the times r to the x. Let's list some points. They only want us to list 3, so our table really allowed us to do that quickly. Of course, you've got other choices too, but here are 3 points. All right, well, let's jump into page 2. We're not going to do all of these, but we're going to do a couple. And the set is quite a bit different. It says for each graph given, match it to the contextual description that fits best, and then label the independent, The independent would be the x-axis, and the dependent would be the y-axis with the proper variables. So tell you what, let's just start with the textual descriptions. Let's maybe take a look right here at A. It says, Becky takes a ride on a Ferris wheel, and her distance from the ground is related to the time that is elapsed. So here's just maybe a little visual picture of what that can look like. We've got a Ferris wheel, of course, and the Ferris wheel might be a little bit closer to the ground, and we could get it a little bit closer down here perhaps. And people will board on. So Becky's going to be walking up, and then she's going to get onto the Ferris wheel. But here's the important thing. There's going to be some distance right here. Later on, as she's rotating, her distance, you have to see, has gotten bigger. She is farther from the ground. Then, as we're rotating around, she's going to be up here. Her distance still has gotten bigger. This is the highest point on the wheel, so she's going to be at this greatest distance, but then she begins to come back down. And eventually, she's going to come right back to the location where she had boarded, where she got onto the Ferris wheel. But of course, the Ferris wheel is going to continue to rotate around. So she's going to continually be rotating around, getting to this high point up here, coming back down. So you can see her distance will be small. It will grow and grow and grow to get to be a largest value. Then it comes back down. And we can ask ourselves, looking at all these graphs, which of these might show that pattern of repeatedly reaching that high point and also having a low point. And I hope you would agree that that would look like 4 right here. 4 is going to be matched right here because, look, you're going to have a maximum height right up here. You're going to have this minimum. It's starting off with Becky being on the ground, and then she's going to get on. But as she begins to, ride, she'll hit a high point, her distance. She's going to come back down here. And, of course, this is going to be time for the independent, for the x-axis, and her distance from the ground is going to be on the y-axis. So let's take a look also at letter B. The number of hours to paint a house is related to the number of workers. Now, we've been talking a lot about discrete versus continuous. Jumping back to Becky's Ferris wheel problem, of course, her distance as she's traveling around, she might be 10 feet from the ground. Of course, she could be 10.1 feet from the ground. That's measurable. It's, every height in between is going to be achieved or will be hit. So it's not like her distance is growing in jumps. Whereas when we're looking at B, it talks about the number of hours to paint a house is related to the number of workers. You can't have fractions of workers or decimals of workers. So as we're looking at this problem, you might guess it's way more likely to be discrete, and it will be. Think about it. If you had to paint a house and if you were the only one working, it would take you a very long time. If you had a friend, a second person, that time would drop. And if you had a third person helping you, that time would drop and drop. So as we're looking at number 3 right here, notice that you could have the hours right here on the y-axis, and you'd have the number of workers here on the x. You can see that maybe you'd have 1 worker, then 2, and so forth. and that time's going to keep going down. Think about it, you might go from 11 workers to 12 workers. You're going to have your time drop down, but maybe not nearly as much of a drop as what you would have seen earlier. I think sometimes workers can even get in each other's way after a while. All right, so we can see that number 3 would be paired here, number 4 right there. Make sure that you do label your axes. Guys, to wrap up, as we're looking at solving equations for the Go, it says for each equation, find the value of x that makes it true. As we're looking at number 7, I think you can see there are 2 terms that are affecting the x, 2 types of arithmetic. It's 3 being multiplied to x. You're also subtracting a 5 from the x. In general, when you have this multiplication and subtraction, when it's looking kind of like mx plus b, that is, what we generally do is we'll get rid of the addition or subtraction first. So look at this minus 5. What's the opposite operation of subtracting 5? Well, we can say it's going to be adding. So we'll do a plus 5 here. We'll do a plus 5 over here. And 37 plus 5 is going to get you 42. So then we have 3 times x equals 42. And tell you what, we can go ahead and do the opposite of 3 times x. That would be dividing by 3. That's going to leave us just with an x. And 42 divided by 3, even if you need some help with the calculator, that would be okay. You can see you get 14. So that's going to be your final answer. Guys, take a look at number 8, however. Number 8 looks drastically different because of this fraction. Oh my goodness, this is not quite the form that we just saw in number 7, where you have a 3x minus 5. The fraction, I think, really jumps out. A fraction, when you've got that x plus 1 divided by 2, I think we're really focused in on that divided by 2. So when you see this division by 2, deal with that first. So when you've got this fraction, what's the opposite of dividing by 2? The answer is multiplying by 2. You can see that a multiplication of 2 would cancel a division of 2. And 9 times 2 on the right is 18. And then we're left with x plus 1. So that's what you need to know for your fractions. When you see that, it looks like it's a much more challenging problem. Deal with what makes that the challenging problem. Deal with that division of 2, multiply both sides by 2. And now what? I'm going to just subtract a 1. I've got x plus 1. The opposite operation of adding a 1 is subtracting a 1. We're going to be left with x equals 17. Finally, as we look at number 9, what you want to do is isolate, isolate a to the x anytime you have something exponential. So I've got 5 to the x plus 1. I'm going to minus a 1 from both sides. 126 minus 1 is 125. And I'll have 5 to a power is equal to 125. Now we're going to do some guessing and checking. So this is where you probably want to take your calculator out, and we'll see what fits. I'm just going to go 5 to a power. Could it be 5 to the second? Well, we know it's not. 5 to the second is 25. Could it be 5? Let's try the next highest power, a 3. 5 to the third, it works. So we're going to say x equals 3, and we are done.